Bradley Hizzard, and I'm doing a recording for the presentation for the ID3 algorithm. And so the first thing was understanding what was the problem that we were dealing with for the assignment, and so we needed to program an ID3 algorithm, and that was by building a model against a training data set, and also then comparing our training data set to our testing data set and reporting the accuracy of the model, and then also displaying the model. And so just initially, just going to explain what an ID3 is and how it works. So basically we have a heap of different features, and all the different features have different amounts of discriminatory power to have the best determination, and we need to basically create the best tree diagram which can explain our data set and which can give us the best predictions. And so the way that we do that is by selecting the features with the most discriminatory power and basically hierarchically ordering them from the most discriminatory power to the least discriminatory power. So in this example here that I've got, we're saying the feature in this circumstance with the most discriminatory power is age. So age is selected as our highest point. We've then split age into three different categories, so less than 30, 30 to 60, greater than 30. So in the data set that we were given, this could be split into the different colours of the mushroom, so white, red, grey, stuff like that. And as we can see, we've now created three branches. Basically, we're starting to create our decision tree. And so the first thing when we go down this less than 30 branch is when we've gone down one branch, we need to now identify what's our next highest discriminatory power, not including the one that we've already used, because we don't want to reuse discriminatory powers because we've already expanded them all out here. So we include our next discriminatory power here, and we keep going down the line, keep going down until we reach the very end. And once we reach the very end, when there's no more features to be used, we do something basically called recursive calling. And so that means once we've gone down, we come back up. So we come back up to the next sub-data or subclassing, and then we go back down another branch from that until all branches are completed. And from there, we hop all the way back up, and we continue down second branches. And we continue that repetition, that recursive calling, until the whole decision tree is completed. Okay, so the next step of ID3 algorithms and what makes it special is when we attempt to establish a leaf node, so that's the very end of a diagram, which is these ones or these ones, it's what are the base cases, what are the reasons that we stop. And so there are three main reasons that we look into in ID3. And so the first one is, so when a group has all the same target features. So for in this example of example 1 here, we have a bunch of different people and we split them up into circles and triangles, and that's how we differentiate them. So we split them up like this, and if we look on the left here, we now realise that this group on the left has all the same target feature values. So what do we do there? So we want to make this now becomes our leaf node. So the target feature value becomes our leaf node, and then we return that value. So another instance of this is in number 2 here, is say we do the exact same thing, we're splitting it into two different types of sets. So we split down the middle, but in this case when we look on the left, we've run out of features, so we don't have any more features to split the data into groups, but we have a square in the middle. And so before we had the majority, but we had all dots, but this time we don't have all dots, we have a square in the middle. So what do we do here? And so in the ID3 algorithms is we can take the majority, the one with the majority of features, values within that group, and we can make that our leaf node, and then we return that value. So in this example, we will take the circle as our leaf node, not the square. And so in our third example, say if we're splitting data, so we do the exact same thing, we split through the data, and we're looking at this group here on the right. And so say we split the data again based on another discriminatory power and predictive power, sorry, and we split the data and we get two groups, and one group has all the dots and the other group has no dots. So in this one we've got nothing in it. And so what do we do there? Like, which feature do we use? So what we do there is we use the parent target feature values as our main leaf node there. So that would be, if say in this example, if we went down to triangle and triangle had nothing in it, what we would do is we would use the feature value from alpha as our replacement for triangle. So what we're looking at now is the results of what I got after using my code. I was coding in Python 3, and so what we can see here is I've segmented it into three parts. So the first part, so this was just giving a template of what the visualization of my decision tree is. This itself is the decision tree. And the final part is the accuracy that we got. So if I just start off with the accuracy, this is meaning for every one prediction that we did, we would get one correct. So every prediction that was made in the test file was seen as correct, so that's why we get 100% accuracy. That means there was no incorrect predictions by the ID3 algorithm or the model. So the next part is if to visualize it a bit more, maybe what the decision means is if we say we initially look by the root, and it's basically working backwards. So the root is our initial point, so our most discriminatory power, and so that would be odor. And so now if you think odor, again, it splits itself up, and it splits itself up into the different categories. And if we are using our template, it splits itself up into the next discriminatory power and any other leaves, so any other endpoints that are left. So our first one, it splits onto the origin 1, and so our origin 1 was 4-point color. And then it also splits up into any other leaves, which are the remaining letters down here. The second one, 4 points, split it up into habitat. And similar with odor, it had its leaves. And then habitat, split it up into cat color. And then cat color, split it up into gill size. And so this is a rough visualization of what the text represents here. So this is the decision tree, the ID3 algorithm that came up, and this model produces 100% accuracy over the test data supplied. And so finally, I'm just going to do a quick overview of the code that I've just implemented. So one of the key issues I had, and something I'm looking to or want to improve later on, was when I was doing the code, I had issues with the initial data set, and I think it was to the length of it, and I had an odd error called white, and it was referring to the values within my within the CSV files, and every time I tried to alter them, it would bring up new values, and I didn't know why, and I never ended up figuring out. But what I did is in Excel, I altered the values and only used the initials and put them all to lowercase, so to more standardise the data. And question marks were still left in there, they didn't seem to have an issue, but it was just reducing them all to initials seemed to fix that issue. And another one was reading the CSVs, I had a bit of an inconsistency. It was a bit hard to, when importing it, it didn't like the hashtag space class, so I altered the hashtag space class to just class in both the test and the training data. And they were basically the only issues I did have, and once I cleared those up, it was much easier to process the data. So there is a bit to go through, but generally I did a heap of different functions, and just to split up to make, because a lot of it was repeated, So because we do a heap of feature gains, and we also do what else? Training models and decision tree outputs. So for these ones, and a lot like calculating the entropy and getting the total entropy, you require the calculating entropy. So it's sort of like embedding within each other, but it means I didn't have to use code multiple times and create a really long Python amount. So the main thing is this accuracy and model. This prints out, so this part here, this part prints out the model, which is what you see down here. And it also prints out the accuracy. The next part, importing the CSV, that's pretty self-explanatory. That imported the training data. So that was the training data. Calculating entropy. Now this just calculates a single value's entropy and not the total entropy, so not the summation. So this does not find our sum, whereas this does find our sum. And this was because some values had a value of 1, and if we know log 1 creates 0, and 0 doesn't add any entropy to this value down here. And so that would just be calling on calculating entropy multiple times, the np log 2 multiple times when we didn't need to, and that's more processing. So I split the two, and by splitting the two it means I don't have to call upon this as much, only when the values need it. So if the value was 1, it wouldn't be called on this, but if it wasn't 1, then it would be called on this, and that saved computation. Feature gain, that obviously finds our information gain, and that uses our entropy here. So you find the initial entropy, and then you find the entropy after it's split, and you minus it, so you find the difference between the two. And the difference is then added to your total gain, and that's what's returned here, just your gain. And we have branch design, and we also have, and that was basically how we design the end parts here and how we get to our leaf nodes. We have our tree design, which it turned, because a lot of the chunk is taken out, so from like the feature gains, it's not actually in the tree design. So the tree design became more of a framework. So it would specify when something needed to be called up, and when that thing needed to be called up, such as a branch design, it would be called up. This still did identify, it basically says which feature has the best entropy, and it would use that one as our main feature, and then that would split down to the next one and find which has the next best entropy, and it would use that one, and it would split and it would split and split. So basically what we talked about before about how a decision tree works. And training, and then our decision tree output, so that gives us the output of each, that gives us the output of a prediction. So after all that's been tested, we get the output. Is the mushroom edible, or is it poisonous? And that's what this did here. And then finally, our function for testing is the exact same thing. We remove the class. We don't want to have the same as training. We remove the class. We don't want to have the predictor in there. We just want to test the data. And then what we did is we compared the data. So we compared the edible and the poisonous of the training of what we trained our data and what it predicted with the tested versions. And so if the trained versions that we did, so if the prediction equaled the tested, then we basically said that's a success and we gained a point. And so the total amount of points was basically returned here as our successful predictions. And what we did after that is our successful predictions was divided by the total lines that there were in the data, and then times by 100 because of the percentage. And that's how we got to our 100%, was through that operation. And then our final line is just a bit of niceties to make it look aesthetically pleasing. And I recall to our function, which is the initial function which calls on everything else. And so that accuracy model calls up right up to here, and this calls on to everything else in the code, and it just works through. And that's about it.